Chapter 5 Cycloalkanes of Organic Chemistry Introduction. The cyclic hydrocarbons having carbon-carbon single bonds and have general formula CnH2n are called cycloalkanes. They are also called polymethylene due to the presence of methylene group in their skeleton. The cycloalkanes comes under the category of aliphatic cyclic compounds. These are so called because they possess cyclic structure and show resemblance with aliphatic compounds in most of their properties. They are also called carbocyclic compounds because their ring skeleton has only one carbon atom. Nomenclature of cycloalkanes. Common name. The name of any saturated alicyclic hydrocarbons is written by attaching the prefix tri, tetra, penta, hexa, etc. to the word methylene according as the number to carbon atoms in the ring. IUPAC name. The IUPAC name of the organic compound contains the following parts. The complete IUPAC name is written as 2 degree prefix plus 2 degree prefix plus word root plus 1 degree suffix plus non 2 degree suffix. Rules for the IUPAC name for alicyclic compounds. First, add prefix cyclo to the name of corresponding state chain hydrocarbon like cyclopropane, cyclobutane, cyclopentane, cyclohexane. Second, the position of the substance present in the ring are indicated by Arabic numerals 1, 2, 3, 4. During numbering, the lowest number is given to that substance whose prefix comes first in the alphabetically order provided that it does not violate the lowest sum rule. Third, if the ring contains more or equal number of carbon atoms than in the substance attached in the ring, then the compound is named as derivative of cycloalkane. If the substance attached to the ring contains the more number of carbon atoms than in the ring, then the compound is named as a derivative of the substance. If, however, more than one alicyclic ring is attached to a single chain, then the compound is named as a derivative of alkane irrespective of number of carbon atoms in the ring or the chain. If the substance attached to the ring contains the multiple bonds or the functional group, then the compound is named as a derivative of the substance irrespective of the size of the ring. Fourth, if the multiple bonds and some other substance are present in the ring, then the numbering is in such a way that the multiple bonds gets the lowest number. Fifth, if the functional group is present along with some other substance in the ring, then the functional groups gets the lowest number. If both ring S and the side chains contains functional group, then the side chain or ring containing principal functional group will act as a principal chain. If, however, the alicyclic ring and the side chain contain the same functional group, then side chain or the ring containing more number of carbon atom will act as a principal chain. If an alicyclic ring is directly attached to the benzene ring, then it is named as a derivative of benzene. If the ring contains functional group which has a carbon atom directly attached to the ring, then carbon atom of the functional group is not considered in numbering. Ninth, if there are more than one functional group attached on the ring, then one of the group is considered as parent and other is named as a substituent. 10th, IUPAC naming of bicyclic cycloalkanes. The hydrocarbons and their derivative contain two or more rings are called bicyclic cycloalkanes. The carbon atoms common to both the rings are called bridge head atoms, and each bond or chain of carbon atom connecting both the bridge head atom is called a bridge. The bridge may contain 0, 1, 2, etc. carbon atoms. The bicyclic compound are named as. Find the name of alkane by counting the total number of carbon atoms as in the two rings. B. Add the prefix bicyclo before the name of the hydrocarbon. C. Find the number of carbon atoms in each of these three bridges connecting the two bridge head carbon atoms and indicated by Arabic numerals 0, 1, 2, etc. Now arrange these two Arabic numerals in descending order and separated from one another by full stops and enclosed in a square brackets, and place these bracket Arabic numerals between name of alkane and prefix bicyclo. If a substituent is present, atoms of the bicyclic ring are numbered. The numbering begins with one of the bridge head atoms, proceeds first along the lowest bridge to the second bridge head atom, contains along the next longest to the first bridge head, and is finally completed along the shortest path. Methods of preparation of cycloalkanes and their derivative. The important method for preparation of cycloalkanes and their derivative are discussed below. First, Front's method, dehalogenation of dihalogen derivative of alkanes. When 1,3 or 1,4 or dihalogen derivative of alkanes react with metal, they get dehalogenated to form cycloalkanes. For example, when 1,3-dibromopropane reacts with metallic zinc, cyclopropane is formed. Second, when 1,4-dibromobutane reacts with metallic zinc, cyclobutane is formed. Note, this method gives good yield only for the preparation of cyclopropane. If terminal halide is present at 1,5 or 1,6 carbon, then reaction forms open chain alkanes. Third, the reaction is comparable to internal Wurtz reaction. Fourth, the reaction proceeds with through the formation of free radical followed by cyclization to form cycloalkane. Second, Dickman condensation. It is an intramolecular accretion condensation which occurs in esters or certain dicarboxylic acid such as adipic acid, pymalic acid. When ethyl adipate is treated with sodium ethoxide, cyclobeta ketoesters is formed, which are hydrolysis followed by decarboxylation form cyclopentanone. This ketone then on reaction with zinc amalgam HCl undergoes crimson reduction to give cyclic alkanes. When diethyl pymulate is treated with sodium dust or sodium alkoxide, it undergoes intramolecular crimson condensation to form cyclic beta ketoester. The cyclic beta ketoester on hydrolysis formed by decarboxylation yield cyclic ketones which on reduction with zinc amalgam and concentrated HCl forms cycloalkanes. Mechanism. The reaction occurs through following steps. First, abstraction of alpha hydrogen by the base to yield carbon anion followed by internal crimson condensation to yield 2 carboxycyclohexanone. Second, hydrolysis of 2-carboethoxycyclohexanone to carboxycyclohexanone followed by its decarboxylation to yield cyclohexanone. Third, reduction of cyclohexanone to cyclohexane, crimson reduction. Third, pyrolysis of calcium or barium salts of dicarboxylic acid. Calcium, barium or thorium salts of dicarboxylic acid or heating strongly from cyclic ketones which can reduce either by crimson reduction or Wolff-Kintzer reduction to cycloalkanes. Wisslin's method for formation of cycloalkanes is based on Planck's rules according to which 1,3-dicarboxylic acid, the geminal dicarboxylic acid in which both carboxylic acid groups are attached to same carbon atoms, on heating undergo decarboxylation to form monocarboxylic acid. Second, 1,4 and 1,5 dicarboxylic acid on heating or distillation in the presence of acetic anhydride give cyclic anhydrides. Third, 1,6 and 1,7 dicarboxylic acid on heating or upon distillation with acetic anhydride give cyclic ketones. Fourth, 1,8 and higher dicarboxylic acid remain unaffected on heating. Damjanov rearrangement. This method provides a pathway for expansion and contraction of cyclic compounds and involves formation of carbocation as intermediate. The carbocations formed may show any of the following reactions: substitution reaction, elimination. Wagner-Merven rearrangement. Ring expansion. When cyclobutyl methanol is treated with concentrated H2SO4 at 443 Kelvin, we get three products 1 and 2 and 4 through ring expansion, whereas product 3 is formed without undergoing ring expansion. Ring contraction. Damjanov rearrangement occurs through ring contraction when the carbocation intermediate has positive change on the alicyclic carbon. For example, first, cyclobutanol undergoes dehydration at 443 Kelvin to give cyclobute 1 in as normal product and 1 cyclopropyl methanol through ring contraction. Second, cyclopentylamine on treatment with nitrous acid undergoes deamination to form cyclopentyl carbocations which forms cyclopentyl alcohol as normal product and cyclobutyl carbinol and methylene cyclobutane through ring contraction. Addition of carbene methylene to olefins. When an alkane is treated with Diazomethane in the presence of ultraviolet light. Photolysis of diazomethane occurs to form methylene, which has to alkene to give cyclopropane derivative. Methylene formed by the photolysis of diazomethane is of two types. Singlet methylene, it is formed in liquid phase photolysis. In single let carbene, the two bonding electrons are of opposite spin. Triplet methylene, it is formed in gas phase photolysis. In this type, non-bonding electrons are present in different orbital. It is also called a biradical. The addition of methylene across the double bond is in accordance with skill theory. Accordingly, to which singlet methylene reacts by one step mechanism, and addition is stereospecific in nature, and stereochemistry of the alkene is retained in product. For example, cis pentene adds upon singlet carbene to give cis product, whereas trans pentene adds singlet carbene to give the trans product. Triplet methylene reacts in two steps, and addition is non-stereospecific in nature. A reaction of either cis or trans, but 2 in with triplet methylene gives the same mixture of cis and trans 1,2-dimethyl cyclopropane. The first step in the addition reaction involves the formation of biradical. It may undergo spin inversion or a free rotation about carbon-carbon bond before it cyclizes to give a mixture of cyclopropane derivatives. Similarly, trans 2-butene also gives mixture of cis or trans 1,2-dimethyl cyclopropane. Second, dichloromethylene CCl2 adds to give alkene when treated with chloroform in presence of potassium tert-butoxide. This reaction is hylostereospecific in nature. Particular stereoisomers of the reactant produce a specific stereoisomers of the product. Simon-Smith's reaction. Free carbenes are not very useful for addition to double bond, since these are extremely reactive and undergo many side reactions, especially insertion reaction. A better method which gives better yield of cyclopropane involves Simon-Smith reaction. In this reaction, alkene is treated with domethane and a zinc copper couple. The actual attacking species is organozinc intermediate, methylene iodide, and zinc react to form carbene, a species called carbenoid. The carbenoid brings out the stereospecific addition of CS2 group directly to the alkene. For example, cis-2-butene reacts with CS2I2 in presence of zinc copper couple gives cis-2,1,2-dimethyl cyclopropane. Similarly, trans-but2-enone reaction with CS2I2 in presence of zinc copper couple gives trans-1,2-dimethyl cyclopropane. Thorpe-Ziegler reaction. In this reaction, a dinitrile in which nitrile groups are attached to terminal carbon atom is treated with a base such as lithium diethylamide to form a cyclic immunonitrile, which is formed through intermolecular condensation. The immunonitrile on hydrolysis forms a cyclic ketone, which on crimson reduction gives cycloalkanes. This method is best suitable for the preparation of large ring compounds. The reaction proceeds through the following sequence. The first step in the reaction, which involves cyclization, occurs under very dilute condition. It is referred as Ziegler high dilution technique. Cyclic rings on to 34 members can be prepared by this method. A reduction of cyclic carbonyl compounds. Crimson reduction. Cyclic ketones, when reduced in presence of zinc amalgam and concentrated HCl, get converted to haloalkanes, in which keto group is reduced to methylene group. Wolff-Kishner reduction. Cyclic ketones on treatment with hydrogen forms hydrogens, which when treated with KOH as glycol from cycloalkanes. Hydrogenation of aromatic hydrocarbons. Cyclohexane and its derivative can be prepared by catalytic hydrogenation of aromatic compounds at high temperature and under high pressure. Physical properties of cycloalkanes. A physical properties. Cyclopropanes and cyclobutane are gases at ordinary temperature, while higher members are liquid. This is because as the molecular size increases, the magnitude of van der Waals force of attraction increases. Therefore, the physical state changes from gas to liquid state. Cycloalkanes are lighter than water. Cycloalkanes are non-polar in nature, and therefore they are insoluble in polar solvents like water, but soluble in non-polar solvents like acetone, carbon tetrachloride. The melting point and boiling point and density of cycloalkanes are higher than their open chain analogies. This is because in alkanes, due to their zigzag structure, they cannot properly fit into the crystal lattice, whereas in cycloalkanes, due to their compact structure, they can properly fit into the crystal lattice. Therefore, due to cross packing, these are stronger intermolecular forces of attraction, and hence cycloalkanes have higher melting points, boiling points, and densities. Chemical properties of cycloalkanes. The cycloalkanes show similarity to alkanes to the fact that all the carbon atoms in these compounds are sp3 hybridized, forming only carbon-carbon and carbon-hydrogen sigma bonds. But all the cycloalkanes are not equally in stable and unreactive. Only cycloalkanes from cyclopentane onwards shows a higher degree of stability and are quite unreactive. As such, these they are not attacked by chemical reagents like strong acids, strong alkalis, common oxidizing agents like MnO4, and powerful reducing agent like lithium aluminum hydride. However, like alkanes, they undergo free radical substitution reaction. On the other hand, due to high angle of strain, the cyclopropane, cyclobutane, and more reactive than alkanes but less reactive than alkenes. Cyclopropane and cyclobutane rings are not very stable and have a tendency to undergo ring cleavage, forming addition products. Thus, they resemble alkenes is undergoing addition reaction. However, they are much less reactive than alkenes. Some of the important chemical reaction of cycloalkanes: free radical substitution reaction. In this reaction, cycloalkanes undergo free radical substitution reaction with halogens at 525 to 575 Kelvin in the dark or at room temperature in presence of addition reaction. Like alkenes, cyclopropane undergoes addition reaction. However, unlike alkenes, cyclopropane does not add ozone and also does not undergo hydroxylation with aqueous KMnO4 solution. Cyclobutane, on the other hand, is less reactive than cyclopropane and hence does not undergo addition reaction under ordinary conditions. However, on hydrogenation at higher temperature, it gives N-butane. From the above discussion, it is evident that cyclopropane is the most reactive of all the cycloalkanes and undergoes many addition reactions through ring cleavage. Cyclobutane is less reactive than cyclopropane and undergoes only addition of hydrogen, while rest of the cycloalkanes are unreactive and do not form addition product. Instead, like alkanes, they yield substitution products. Relative stability of cycloalkanes based strain theory. The relative stability of different cycloalkanes can be explained on the basis of their angle of strain, which is introduced by Bayer. He explained the difference in their reactivities of different cycloalkanes on the basis of his pair strain theory put forward in 1835. The main points of this theory are: in cycloalkanes, each carbon atom is sp3 hybridized. Therefore, it should be bonded to four other carbon atoms, and angle between any pair of adjacent bonds should be 109.5 degree. Cycloalkanes, due to their cyclic structure, are planar in nature. The bond angle between adjacent carbon atom in the ring are no longer equal to normal tetrahedral angle. The deviation of the angle varies with the size of the ring. Any deviation or distortion from the normal tetrahedral angle causes a strain in the ring, which is known as angle of strain. Angle of strain is found by the formula equal to 1 by 2 bracket 109 degree 5 minus bond angle in the planar ring. For the greater the deviation from the normal tetrahedral angle during the formation of a ring, greater will be the angle of strain, and hence greater the reactivity of cycloalkane. The ease of formation of cycloalkanes is directly related to stability of the ring. Stability of the ring is inversely proportional to angle of strain. 6. The more the stability of cycloalkane, the more easily it is formed. Evidences in favor of Baer strain theory. The following facts favors the Baer strain theory. Reactivity of double bond in alkanes. According to Baer strain theory, double bond is treated as two-membered ring structure having bond angle 0 degree. So the angle of strain is alkenes. As alkenes have very high angle of strain, hence it proves the unstability and reactivity of alkenes. Reactivity of cyclopropane and cyclobutane. Both cyclopropane and cyclobutane have high value of angle of strain. High value of heat of combustion. So both cyclopropane and cyclobutane are unstable. Limitation of base strain theory. The base strain theory cannot explain the following facts. Stability of cyclohexanes and higher member ring. According to base strain theory, cyclohexane and high member rings have high angle of strain, so they should be unstable as per base strain theory. But cyclohexane and higher member rings are stable. Hence, base strain theory cannot explain the stability of cycloalkanes and higher member ring. The bent angle is determined by drawing tangent through the old position of the carbon-carbon bond in cyclopropane.